everyone. Thank you for joining. And I'm Krishna Acharya. And welcome to my PhD defense on recommender systems with fairness considerations and strategic agent dynamics. Recommender systems are everywhere and they shape what billions of people see each day, from what we watch on Netflix to what we see on YouTube and to what we buy on Amazon. And what's happening is these systems are getting increasingly personalized and capable of understanding user intent. Now, under the hood, any platform, be it Netflix or YouTube or Amazon, all have the same structure. We have users on this platform who consume the recommendations, and we have items such as movies, videos, or products. And we have a model which takes in the user's interaction history and decides what they should see next. Now, these recommender models have come a long way over the years. In the early days, we had simple collaborative and content-based filtering systems. Then in the late 2000s, we had this Netflix prize competition, which established matrix factorization as the state of the art. And around 2015, platforms began collecting a lot of user data, like their clicks, watch time, their purchases, and this growing volume of data paired really well with deep learning methods, which became the state of the art at the time. And from 2019 onwards, we have these transformer-based models like SASREC and BERT4REC. And what they do is they adopt this transformer architecture and become really good at modeling temporal order or like user session intent. And most recently, we have these LLM-based recommenders, which can reason over item metadata, such as the item's text or image. So what I want to say is, over the years, we have had these advances in model capacity, but they bring about new challenges around user fairness and strategic behavior, which are the focus of my dissertation. And my dissertation studies three challenges in recommender systems. First is to ensure fair performance across heterogeneous user populations, and then how to characterize how strategic content producers shape their item catalog in response to the recommender, and understanding these in the setting of large language-based recommendation. My talk is divided into three main parts. In part one, we'll focus on user fairness. And the key insight here is that models that are optimized for average case performance can have disparate outcomes on user segments. And we will develop the theoretical foundations for this in an online learning setting. And then we will look at methods for minimax group fairness in a sequential recommendation. In part two, we will shift to the item side of the recommender system, and we'll study how economically motivated producers adapt their content in response to the recommender, and we'll understand the item catalogs that arise from this competition. In part three, we will focus on LLM-based recommendation, which are the current state of the art, and I will present our paper gloss and show how representing items through rich semantic content like their text greatly improves recommendation metrics. And finally, we will conclude and I'll discuss new forms of producer manipulation that these LLM-based systems are susceptible to. With that, let's begin with the first contribution, which is Oracle efficient algorithms for groupwise regret. And this work establishes the foundations of minimax fairness in an online learning setting. Let's first briefly recap the notion of online learning and regret. In online learning, the data arrives one by one, and we need to make predictions on the fly. For example, we have patients arriving here, and we need to estimate their healthcare costs. For this, we use a learning algorithm that uses the data seen so far and makes a prediction, a PT for this individual. And then the true label YT is revealed and the algorithm attains a loss L. Now, our goal in online learning is to minimize a notion called regret, which is the difference between the algorithm's cumulative loss, which I've highlighted in orange, and the best fixed policy in hindsight, which I've highlighted in green. And the goal is to obtain a sublinear regret. So what that means is, in average, we want this quantity to go towards zero. And that's what sublinear regret guarantees. Now, the natural next question we ask is, what if we care about performance not just overall, but on every subsequence of individuals? And this brings us to the notion of group-wise regret. Here too, we have individuals that arrive one by one, but along with their features, we get to observe group memberships. For example, in this figure, we have time intervals in which we see the old age group, and we have this purple interval in which we see the young age group. So our algorithm, upon seeing these features and group memberships, then makes a prediction PT, and as usual, we obtain a loss L. Now, our goal in group-wise regret is to obtain sublinear regret, not just for the whole sequence, but over every sequence in which this user group arrives. And so, in a sense, we are trying to obtain sublinear regret, which is little o of tg, where tg is the total time interval in which we see users from this group. Now, if the user groups were disjoint, this is a very straightforward problem because you can run independent learning algorithms. But because groups do intersect, we need something smarter. Of the feature, right? Now, there has been prior work in this space, and most recently, Blum and Licoris showed that there's an algorithm that has sublinear group-wise regret, but this comes at a very high cost, which is that their construction, the runtime for their construction scales in the size of their hypothesis class. So because they use G times H sleeping experts. And so what happens is you can only run this algorithm for a small discrete hypothesis class. And even for a very simple linear model, which is continuous, we cannot run this algorithm. Which brings me to our algorithm. And the best way to understand it is by this simple use case. Here we have an individual which belongs to the white race group and the young age group. And to get a prediction, what we do is we query all the active group experts for this individual, which over here are the young age group, the white race group, and also an always active expert, which is trained on all the data seen so far. And to get a prediction, what we do is we query all three of them, and we use a meta learning algorithm called add a normal hedge, which can aggregate these predictions to make a final prediction. Then, as usual, we observe the true label. And importantly, we only update the internal states of the active group experts. So what this means is, unlike prior work, the way we use add a normal hedge will not, the hypothesis class will not enter in this aggregation. So our runtime scales only with the number of groups, and it is Oracle efficient in the hypothesis class. In our experiments, we provide the first practical algorithm for online linear regression with group-wise regret. And we evaluate performance by comparing our algorithm versus the benchmark of online ridge regression. And our evaluation uses real-world data sets like the census income data sets and the medical cost data set. And on the right, I've compared, on the y-axis, we have cumulative regret, and the x-axis has the time step. And what we see throughout is on all the three age groups, our algorithm, which is a solid curve, has lower regret than the benchmark, which is the curve with cross marks on it. And we observe similar regret curves for the BMI-based groups as well as other data sets that you can find in the paper. With that, now let's continue our discussion on user fairness. And I will discuss my paper on improving minimax group fairness in sequential recommendation. And this work looks at robust training methods for training deep learning-based sequential models. Let's first understand this sequential recommendation task. Here, imagine you have a user that has uh, like purchased a monitor, then a mouse, then printer and copier paper. They're most likely to buy maybe a keyboard or printer ink cartridges. And this is exactly what is the task of sequential recommendation. We are trying to predict a ranked list of items that the user is most likely to click on. And the dominant architecture for this is is a model called self-attentive sequential recommendation. And this is essentially a transformer model. And it's trained by taking the sequence of item IDs as input and predicting the left shifted version of this sequence. And this is very similar to the next token prediction task in language modeling. The only difference is that our vocabulary here is like the IDs of the items in the catalog. Um, this model is really good and it has been deployed in many production-based systems. It obtains very high metrics, but sometimes high metrics can hide disparities on user segments, which brings me to the topic of user fairness in recommendation. Now, both data and algorithms can lead to unfair outcomes. We can have a model that performs really well on aggregate, but when you measure its performance on user segments, we have degradations. A well-known example in this field is a concept known as popularity bias. Here we have a plot of number of interactions on the y-axis and the item IDs on the x-axis. And what we see is a small number of items known as head items like dominate most of the interactions. And this is natural because there are they correspond to things like popular movies or TV shows, whereas most other movies or TV shows have a low number of ratings or interactions. So as a result, what happens is the recommender system can skew towards showing popular content only. And to give you an example, here we have a user which has like interacted with 13 niche movies and 70 popular movies. And so it expects that in its recommendation list, this kind of split would be represented. But in the extreme case, what can happen is you can have only popular movies being recommended, and that leads to a drop in the user's recommendation quality. Another very closely related issue is the issue of cold start. Here we have users which are new to the platform, so we don't have like interactions for them, and these two also get a low number of like low recommendation quality. And this brings me to the notion of group fairness. It is one way to tackle these disparities. Over here, users are segmented on features like sex or race, or even functional characteristics like the number of views or the number of purchases they've had. And the goal in group fairness is to equalize metrics across groups. And ideally, so over here, like you have the true positive rate, so the recalls for group A and group B, and you can see how they have kind of adjusted the thresholds to equalize them. Now, so ideally, the best way to do it would be to reduce the loss for the disadvantaged group. But what can end up happening is that algorithms can inflate the loss of the advantaged group in order to equalize metrics. And this is clearly something which we don't want to happen. And there's also deeper issues, such as if you have users lying in multiple groups, it can be statistically hard to satisfy group fairness. And there's also legal prohibitions on using certain characteristics like sex or race in either training the algorithm or like post-processing the thresholds. And this motivates the notion of minimax group fairness. And here, instead of equalizing metrics, what we're trying to do is minimize the loss of the worst performing group. And formally, we are searching for a parameter theta star that can minimize the maximum group loss. And there are many methods that exist to approximately solve this objective, approximately because L could be non-convex and a deep learning model. So, and the most prominent of which is a method called distributionally robust optimization. And to understand this, let's briefly recap standard training. In what happens in standard training is, or like formally known as empirical risk minimization, we are trying to minimize the average loss over the training data. Whereas in distributionally robust optimization, we are trying to minimize the worst case loss over distributions which are close to the training distributions. And that's captured by this image, which is like this set of shifted distributions. Now, existing approaches for distributionally robust optimization have been applied to recommendation. And most recently, Wen et al. Proposed this algorithm called group DRO and streaming DRO. And the way these work is they have two main components. There's a inner maximization, which I've highlighted in green, and an outer minimization, which I've highlighted in yellow. And what these are doing is they're building a weighted mixture of user group distributions. And these weights are upweighted in a exponential weights fashion so that groups with larger loss have their group weight increased. These group-based DRO methods now they do work and they have been applied previously in the context of recommendation, but they have major limitations. The first of which is you require group memberships upfront during training time. Let me explain why this is a problem. In the typical ML lifecycle, we have like model training, evaluation, and finally deployment. And after deployment is when we typically observe these segment-wise degradations, or essentially that's when we detect that these groups are having a degraded performance. So there's that issue about not having group memberships during training. Another issue, even if we knew these groups upfront, is that users can lie in multiple intersecting groups. And as you saw in the earlier slide, we need to maintain a probability distribution over these groups. So one naive way would be to atomicize all intersections. But as you can imagine, this scales exponentially and this quickly becomes impractical. And this brings us to the idea of conditional value at risk DRO or CVAR DRO. It is a completely group agnostic methods and no group membership is required during training time. And its objective is to minimize the loss of the worst performing alpha fraction of examples in each batch. And the idea is that this way you can automatically capture users with like a high loss and kind of improve metrics for them without using explicit group annotations. Let's now look at the experiments where we compare these DRO methods head to head. We use two real-world data sets, the Retail Rocket and the Movie Lens 1 million data set. Retail Rocket is a popular e-commerce click-based data set, and Movie Lens is a very popular movies data set. And for evaluation, what we do is we hold out the very last item in each user's sequence for testing, and we measure the metrics we measure are NDCG. It's normalized discounted cumulative gain. It's a ranking metric which is essentially capturing how high is the test item in my predicted rank list. And one more key part of this experimental setup so far, we have discussed groups. We have to also define user groups. And the first user group we consider is based on the ratio of popular items in that user's history. And so we call a user a niche, diverse, or a popular item viewer if this threshold of popular items is low, medium, or high. And the second kind of grouping we consider is user interaction length. And here we categorize a user as what do you say, short sequence, medium sequence, or long sequence user, depending on its interaction length. Now, one thing to note is that depending on the threshold we use to define these user groups, users can end up lying in a slightly different bucket. So what we do is we run experiments across three different choices of thresholds and show that our findings are consistent across each of them. It's not like we were lucky with any particular group split. With that, let's discuss our main experimental results. In our first experiment, what we do is we study a simple setting of non-intersecting user groups, and we compare metrics on popularity-based user groups. And here we see that all the three DRO methods, which are in the last three rows, improve over standard training or ERM. And this is both on, on all of the groups and as well as on aggregate. And CVAR DRO comes out on top with the highest NDCG. And this is true even for highly imbalanced group splits like the rightmost table, where we have certain user groups that have much smaller sizes than the like GPOP 1080 represents a very imbalanced group split. And even in this case, CVAR has the best performance. Whereas if you look at group DRO and streaming DRO, their numbers are pretty similar to standard training. So it's like no improvement has been seen at all. We then look at the harder setting of ensuring minimax fairness across both popularity and sequence length groups.
Sorry,
And this
Krishna,
is
could you just go back? I was trying to parse the table. What are the numbers in the table?
these are like NDCG numbers. Yeah, so I don't
Okay.
want to know what the table represented.
And the columns are different groupings according to
The
different
thresholds of
thresholds you chose.
yeah,
Okay. And so like the C bar numbers are higher across all of the groupings than the ERM numbers.
right.
So does that imply that that sort of the ERM optimization is just failing? Like, does the C bar have a higher marginal accuracy than ERM? Like, is the CVAR method optimizing the ERM objective better than the ERM method is?
So the way that we measure it is like we ERM is standard ERM, standard training. CVAR has this kind of tail loss or like a certain fraction of examples in the batch which are used for backpropagating. So what ends up happening is after you train it and then you measure these metrics on test according to these user segments, we see that for like let's look at one of the splits, which is GPOP 33. This is like when we have the most balanced group splits. We see that on the niche, diverse, and popular user groups, these numbers are better than standard training.
Okay, so not only according to sort of the CVAR metric that you are optimizing for explicitly, but also according to the ERM metric. Is that right?
Right. Yeah. Cool. So this was in the simple setting in which we only cared about improving numbers for one user group, which is like popularity based. We now discuss the harder setting, which is ensuring minimax fairness across both popularity and sequence length groups simultaneously. And remember that these do intersect. And on the right, I have two plots. The first measures the performance. So the y-axis is the percentage improvement in NDCG, percentage improvement over standard training, and the x-axis has group names. And the first plot has all the popularity-based group numbers, and the second one has the sequence length group metrics. And what we see throughout is that CVAR DRO, which is in the blue bar, is always better on 5 out of 6 of these. So let's kind of motivate why this is happening. And one issue with group-based methods is that we must commit to one of these atom choices. So we must either commit to popularity based or sequence length based groups at training time. And we show in these plots that the kind of group you commit to results in a very different metrics. So it's like highly sensitive to the choice of the atoms uh, that you have in the loss. Whereas CVAR DRO, which is entirely group agnostic, doesn't require these annotations at all, and it outperforms both on aggregate and on 5 out of 6 of these user groups.
Sorry, I didn't understand why for regular DRO you need to commit to either the popularity based or length based segmentation.
Right. So GDRO and SDRO, these are both like they require group annotations because you're kind of maintaining a probability distribution over each of them.
right?
So,
Yeah, so I get that you need the group annotations.
right.
But like, why couldn't I handle six distributions that,
Yeah.
um,
So what I'm saying is it's very sensitive to what kind of how you choose your atoms is the takeaway from this I want you to have. Is like suppose you ended up choosing those six versus those three, or like the final metrics are very sensitive to these, and you can't know them upfront before you train, is the point I'm trying to.
okay, so I could run DRO with these six groups and it
Yes.
would work fine. Okay.
Yeah.
And it did you? Like, is that what we're seeing on the plot?
Yeah. So on the plot on the left, plot is like when we just so you see each of those five colors, there's like a small subscript which says popularity or sequential. So what that is saying is the choice of atoms that I had for the loss.
So
uh,
for none of them did you choose all six?
there is an experiment in the paper which does that, but this is when you choose either one of them.
Okay.
Yeah, right. So the main takeaway I want you to have from this is that standard training can lead to poor performance on atypical user segments, and group TRO methods help to mitigate this. But the disadvantage is that we require group memberships upfront during training. And if you have here, we just had two user groups, but imagine that you had 10 different user groups, and you then have to think about how you would scale to those intersections. And also, as we saw in the like group splits which are imbalanced, the performance can really degrade. Whereas CVAR DRO does not, is entirely group agnostic and outperforms both of these group-based methods, both on aggregate and group-wise.
And so,
And
sorry, so just so I understand that, like, if these were like convex models or something that you could optimize exactly,
right.
what you're describing shouldn't happen. Like, it shouldn't be possible to outperform ERM on like the ERM objective. Is that right? So, like, part of what you're seeing here is sort of the method is like better navigating, the non-convex optimization landscape, but for reasons that are not entirely understood. Is it something like that?
Yeah, so there are like two. So first of all, the model is a transformer. So there's like that non-convexity. And there's also, so what we do in ERM is just standard the ERM objective, but eventually what you measure is these metrics on all user groups. And CVAR is similarly a CVAR objective, and in the end, you measure performance on user segments. So, like, yeah, in a sense, like if you are exactly sure that these are the groups you have to optimize for, group-based methods should do better, but it turns out they do not in practice.
And even ERM, because on your table you showed better performance on every group. So
Yeah,
it's not that it's sort of
yeah,
reducing the
it's
max
also
loss.
it's also beating overall. Yeah, yeah.
Okay.
Um, And that brings us to the end of the user fairness section. Now we will shift to the item side and study how economically motivated producers adapt their content under the recommendation mechanism. And this is based on my paper on producer equilibria and dynamics in recommender systems. And let's first understand this competition. We like usually we still have users on the platform, but we have their embeddings which are represented in this embedding space by the three vectors. And then we have content creators here, Alice and Bob, whose content vectors also lie in the same embedding space, which are represented by the gold and blue arrows. And then based on vector similarity, what happens is the recommender recommends Alice's content to two users, and Bob's content only reaches one user. And so Bob, being strategic, will now think about how to kind of shift his vector to match more users. And so this model is at the heart of the competition that we study in the paper. And formally, we have K users with embedding CK and N producers each choosing a content strategy SI. And each producer's utility is then the total user engagement. And you can think of total user engagement as a proxy for real world metrics like watch time, where like a producer on YouTube doesn't care just about how many clicks they have had, but what is the total watch time for its videos. And so mathematically, this utility is modeled as a product of two terms. The first term is the probability that a user sees producerized content. And the second term is kind of how aligned is this content to my user embedding vector. And so that's captured by the relevance score. Now, when it comes to the probability or of, so where were we? Yeah, we were discussing different choices for this probability of the user. Aaron, did you get this slide or did this slide cut off?
I saw the beginning of this slide, um,
Right.
but maybe it's helpful if you walk through the what the utility function is again.
Yep. So like we have K users on this recommender with embedding CK and N producers each choosing a strategy SI. And the utility is kind of the total user engagement for this producer. And this is kind of a proxy for real world metrics like watch time, where we are not just optimizing for clicks, but also how long was all of my content watched. And formally, it's given by product of two terms. The first one is the probability that a user case sees the producer's content. And then there's a second term, which is kind of the relevance score, which is how well aligned is uh, this content to my embedding. And there are various choices for this probability or serving rule. And we study three different families for it. The first one is softmax based, and we study both temperature scaled and top K filtered softmax. And like a note about this is lower values for temperature or lower top K values result in a more greedy serving rule. And what that means is that uh, by being greedy, you're trying to serve only the most aligned content to the user. We also studied two other serving rules. The loose rule, which serves content linearly proportional to the relevance score, and the round robin rule, which is equally likely to show any producer's content. So you can think of this like a random serving. Uh, with that, our main result is that for all of these serving rules, the Nash equilibrium must be supported on the basis vectors of the embedding space. A quick recap on Nash equilibrium. It's a situation in games where no player can benefit by changing their strategy, given that all the other players are holding their strategy fixed. A classic example for this is the Prisoner's Dilemma game, where the Nash equilibrium is when both players end up confessing. And I've kind of shown the dynamics to Nash equilibrium by those arrows. Now, for our game, we show that at Nash equilibrium, each producer focuses on a single embedding dimension, and which I've denoted by the three cross-marked vectors in the embedding space. So with this structural result, we kind of ask, what does the resulting item catalog look like at equilibrium? And quantitatively, there are two very different equilibrium outcomes. The first one is when producers specialize. And this means that each producer is concentrating on a distinct niche, and this yields a heterogeneous item catalog at equilibrium. The second extreme is homogenization or like no specialization by producers, where all producers kind of converge on the same popular content, and this leads to an item catalog collapse. And what we show is analytically is that the linear serving rule leads to specialization, whereas the round robin rule leads to no specialization. And whereas for the softmax family, this specialization depends on both the temperature and top K values. And we run experiments to look at the grade, like what degree of specialization uh, occurs with each of them. Now, in our experiments, we use user embeddings from the Movie Lens 100K, and the Amazon ratings data set. And producers' competition is modeled via best response updates, which is kind of like holding the one all of the other producers fixed, one producer changes its strategy and so on. And at Equilibrium, what we measure is both the diversity of the item catalog as well as the producer utility. And our first finding is that softmax serving rules, as they become more greedier, the catalog diversity increases. And so the blue bars in these figures kind of represent the user mass per embedding dimension, and the red bars are the producer strategy per embedding dimension. So as you can see, for a very high softmax temperature, all the producers kind of target one embedding dimension. And as this temperature decreases, you have producers spreading across the embedding dimensions. And this results in a diverse catalog, which is great for the user's needs. Now, when it comes to the producer side, even a greedy serving rule leads to a higher utility. In the plot below, the x-axis is the softmax temperature, and the y-axis is the producer utility. And you can see how low values for temperature as well as lower top K values result in higher producer utility. Now, the only kind of drawback with this is that greedy serving uh, is leads to lower convergence to Nash equilibrium. It's less likely to converge, but that's about the one drawback with greedy or serving rules. And this kind of brings us to the end of our item side of the recommender system discussion. And now I will discuss LLM-based recommendation.
Before you want any question about the convergence to equilibria, like, what do you mean when you say that it's converging to this equilibrium? Is it something limit running this process?
Yeah, so how we model producer competition is like they run best response dynamics updates, and when that kind of there's no incentive for any of them to update the strategy anymore, that's what we call like conversions. Yeah.
Maybe to follow up on that. Are the best response dynamics are like full information in the sense that the producers are just they know the user embeddings and they're best responding to each other, or is there some learning going on?
So it's full information. Yeah.
And this is like a simulation setting, so you run it for different forms of serving rules.
Right. So this is mainly for the figure on the right is for softmax serving. Linear and round robin kind of one shot converge to equilibria. Yeah.
Just one clarification question. So there's a higher temperature means does that mean the streaker, the softmax that you get as you update?
So higher temperatures means like it's more towards random. It's like exploring a lot, whereas very low temperatures like very most aligned content. So this brings us to the end of our item side, and now let's discuss LLM-based recommendations. In my previous work so far, item representations were learned from scratch. And so we learned basically we learn an embedding for every item in the catalog. So now we ask, what if we represent items directly through semantic content like their text and use large language models for recommendation? And as we see in my paper on gloss, that this greatly improves recommendation metrics. And our task is still sequential recommendation, and we want to predict the most likely next item for the user. But we are doing it slightly differently from what we have done so far, which was ID-based methods. So all of the previous works were in this space of ID-based recommendation, where the way these work is the model takes in the user's most recently interacted items and then passes these most recently interacted items through a transformer, and that outputs the user embedding. Now, to retrieve similar items, what they look up, they kind of look up what are the closest items in an nearest neighbor index, and then that's how they generate the kind of rank list, final rank list for this user. Now, the main benefit of these ID-based systems is that they're relatively small. They're only like 5 to 10 million parameters, and that means they're very fast to train, and they're also very fast to run inference on because you have these items which are stored in this nearest neighbor index, and that can be done offline. And when a user request comes in, all you need to do is look up the user embedding and match it. Now, coming to the drawbacks of this approach, the main one is that we need to learn embeddings from scratch for each item. And these do not generalize even on the same surface. So if you have like YouTube search versus YouTube home feed or watch next, each of them have like different, you end up learning different embeddings for the same item across surfaces. And so there is that issue of generalization. And another very closely related issue is cold start. So as soon as you insert new items in the catalog, like new videos or TV shows, or you don't have embeddings for these. So there is that issue of you need to then somehow get interactions for this new item before you can really learn its embedding. And we also have lower performance for new users on the platform because of their limited interaction history. So this brings us to the idea of LLM-based recommendation. So we have these models which are pre-trained on like internet scale corpora, and kind of they have an idea of what user intent looks like. So why don't we just use them to generate the next item text? So that's exactly what LLM-based recommendation is. We kind of serialize the user, all the items that the user has looked at, and we ask the LLM to generate the next item's metadata. And it's still not so straightforward. There are a couple of design choices. First of all, we need to kind of incorporate our catalog's knowledge into the LLM. So the LLM doesn't know what movie IDs on like or like song IDs on Spotify mean, or what movie IDs on Netflix mean. So you kind of need to incorporate this catalog knowledge into the LLM. There are a couple of approaches here. You can do it in context or with retrieval augmented generation. But what is the most kind of dominant way to do it is really fine tune it with our catalog data. And there's also the question of what generation strategy should we use, like should it be deterministic or sampling based? And finally, like how many candidate text do we generate for this item? So if we generate too few text, we can end up missing the target item. And if you generate too many, these LLM-based models are kind of inference bottlenecked. So we can't end up generating too many of them. And there's another design question on how we kind of ground back these candidate text to the item catalog. And for that, we'll look at different retrieval methods. And our gloss, which is generative language models with semantic search, kind of follows this pipeline. And we use models from the Llama 3 family. We first verbalize this user's interaction history into text using the item titles. So whatever is like, think about this is shampoo, we kind of get this title for the shampoo and kind of stick that into the user's interaction history. And so this forms all the fine-tuning data for the LLM. And we then fine-tune it with, first of all, we were in a resource constraint setting, so we use like quantized versions of these models and with low rank adapters. So once we end up fine-tuning it, we freeze these adapters. And at serving time, when a user request comes in, the LLM then generates k different completions for the item title. And each of these item titles are then matched to the actual items in the catalog using a retrieval method. I'll first give a quick note on candidate text generation. So there are, I think, two main
Sorry,
paradigms
and
here.
quick question. The reason you need this last matching step is because the llama model will just like output things that are not real items, and so you just need to find.
Exactly.
Okay.
So it can, so what it can closely match it, but not exactly. So we finally want to have items in the catalog. Um, So when it comes to candidate text generation, there are two main paradigms. One is deterministic and the other is sampling based approaches. So in deterministic, which we kind of use beam search decoding, and the way this works is it maintains the top k most likely completions at any given time step. And there's also sampling based approaches like temperature and top k sampling, which are indeed parallelizable, but what happens is in our recommendation task, it's too noisy for our use case. So we evaluate it on our validation sets and it does not do so well. And when it comes to this retrieval part, which of like this candidate text that's generated, now we need to kind of find it in our item catalog. There are two main approaches. One is like sparse retrieval. This is like simple keyword matching and like term frequency overlap. And there are like classical algorithms for this, such as TF-IDF or BM25. But what we use is this a dense retrieval approach, where what we're doing is we get this candidate text, we encode it into a candidate embedding, and we use that to search the closest items instead of doing like keyword matching or things like that. And in particular, we use these models called E5 small and E5 base. And these are contrastively trained like encoders, which are really good at understanding text similarity. Um, let's now discuss our experiments. We use three Amazon-based ratings data sets. We use the beauty, toys, and sports categories. And as usual, we apply the leave one out split, where we hold out the very last test item for like evaluation. And the metrics we measure are recall and NDCG. And all recall, as it kind of measures how whether this held out item appeared in my rank list, and NDCG measures whether it's ranked highly in this rank list. And our first main result is that our first main result is that Gloss outperforms all of the ID-based benchmarks that we compare to. And these gains are substantial. Like there are double-digit improvements on both recall and NDCG across all our data sets. And the last three rows kind of denote Gloss instantiated with different llama backbones. So there's like 8 billion kind of represents when we use the 8 billion parameter model, and 3 and 1, so on. And we end up seeing that Gloss 8 billion has the best performance amongst the three of them and also across all of the sequential benchmarks. Now, this is when we compare to ID-based systems, but to keep it more fair, we also evaluate performance against like the state-of-the-art LLM-based recommender benchmarks. And here,
Sorry, can you just, maybe you said it already, but remind me what these metrics are measuring? Like you have on held out data, like the next item the person actually bought or something, and you want to see if in the top 5 predictions you predict that item, something like that.
yeah, exactly. So the way, so we have held out the very last item, which is the test item, and we are measuring in our 5 predictions, does this item end up lying in it? And we measure the average of it over all the users. That's what recall measures. NDCG would just be like discounted by where it lies in those 5 positions.
Okay, and this is unrelated to your work, but like, is this a good evaluation metric? Like, presumably, a recommender system affects sales. Like, if I recommend you something that it turns out when you click on it is appealing to you, you buy it when you wouldn't have otherwise bought it. And so, in order to do that, I might not want to just predict the thing you would have bought absent my intervention. I didn't need the recommendation system for that.
Right. So I think what you're hinting at is so these metrics like NDCG, recall, there are a bunch of others like reciprocal ranks and all. These are kind of offline metrics which they kind of people in academia and industry use to gauge whether it's worth deploying. And after you deploy it, they measure these kind of like watch time or whether they ended up buying new items. So those are metrics which are in a different phase, kind of the deployment phase of it. And there are like different algorithms to optimize for those, I believe.
Okay. But like, it's just not obvious that like predicting the thing that you would have done absent my intervention is the goal of a recommender system. But yeah, it's orthogonal, so you can go on.
Yeah, it's kind of in sequential recommendation, that's kind of the task because we are trying to we have held this out and we want to know whether you're going to predict this item or not. So that's how sequential recommendation is modeled. I think there are other notions like sequence agnostic, like we don't care about sequences there and we can.
Yeah, I mean, I'm not like the technical framing makes sense. I'm just saying like if I recommend to you to buy the thing that you were going to buy anyway without my recommendation,
Yeah.
you might well buy it, but that wasn't like a useful intervention.
Yep, yep. Yeah. Uh, with that, we were discussing, so we saw that the performance for gloss on ID-based benchmarks is like we have double-digit gains on these retrieval and recall metrics. So now we compare, which is a slightly more fair comparison to LLM-based benchmarks. And here too, we see that our recall is much better than these state-of-the-art LLM benchmarks. It varies from all the way from 4 to 20%. But when it comes to NDCG, our results are competitive, but they're not state of the art. And here I want to point out that some of these benchmarks, like Llama for Llama Rec, actually use a re-ranking model. So they use like a LLM twice. They use it as a judge even. So there's we don't have a re-ranking phase. So that kind of points to why our ranking metrics are slightly lower. And we also study the importance of this dense retrieval that we had at the final stage of the gloss pipeline. So here, what we do is we kind of ablate it. We replace the dense retrieval with a sparse retrieval model, and we see that dense retrieval is very important in our use case for grounding the items back to the catalog. And if you just look at the numbers on NDCG, there's like a up to 12% increase in NDCG just by using dense retrieval. And I want to point out that this dense retrieval infrastructure is kind of always available in industry pipelines. So like no extra cost, so to say. So it's not like it's much slower than these sparse retrieval methods. And finally, in the spirit of fairness, we also evaluate performance on users with different interaction lengths. And so what we do here is we measure our glosses metrics for short sequence users, medium sequence, as well as long sequence users. And what we see that is that these metrics remain strong across all of these user groups. And no user segment is being sacrificed for aggregate metrics. And in fact, if you look at the toys and sports data sets, here we see that short sequence users actually have really good performance. And with that, the main takeaways I want you to have is that high quality text generation is achievable on very modest hardware. All of our experiments were run on a single A5000, and we use quantized low rank models. And we also use like attention speed, paged attention, which is like an inference speed up technique. And what we show is our gloss pipeline is state of the art. It beats all ID-based benchmarks as well as LLM-based benchmarks. And in this grounding step, we show that semantic search or dense retrieval really brings you these ranking and retrieval gains. And when we measure performance across users of different sequence length, we see that these numbers are pretty strong. It's not like any one user segment is sacrificed for overall metrics. And finally, as these LLM-based recommender systems are now like becoming the norm and rapidly adopted in the industry, it's important to consider the risks. And I'll discuss two kind of future directions in this space. So first, like tying back to the producer equilibrium dynamics work, there's like producers here are like economically motivated. Think about like a seller on Amazon. They have a product out there. They want to increase visibility and revenue for this product. So one such way in which they can manipulate or like boost ratings is a shilling attack. And what this means is that the seller is introducing fake users to kind of click on that target item so that you can boost the visibility. And LLM-based systems are especially kind of biased to latest tokens in the context window. So then there is like recency-based shilling attacks that they're especially susceptible to. Another risk I want to highlight is semantic rewriting. So think about a seller who has like low exposure, like engagement for their item. What they can do is like rewrite their item's title and description to kind of match the most popular items or like just try to match the trend. Now, this kind of rewrite is harder to detect and sometimes even more successful than shilling attacks where you have to launch these fake users. And it's even harder these days to make out whether these rewrites were genuine, like the user, like the producers kind of genuinely changing the item description, or are they doing something malicious like stuffing keywords into their descriptions to increase exposure? And this brings me to the end of the defense. The papers I discussed today span three themes in user fairness and then competition and item diversity, as well as LLM-based recommendation. During my PhD, I've also contributed to works in algorithmic fairness, game theory, and differential privacy. These have been peer-reviewed and published. And of course, all of this work is a collaborative effort. And I'm really grateful to all of my co-authors from Georgia Tech, from UPenn, and from Amazon for all of their contributions throughout the years. And with that, I also want to thank my committee for all of their valuable feedback, time, and guidance. And now I want to open the floor for questions. And thanks everyone for listening.
Yeah, this kind of questions from the audience. Is there anyone on?
Oh yeah, I should check that. Online questions. Looks like there's no online.
I mean, I know Aaron is on.
Aaron is online. Yeah.
Sure, I can ask a question. Just yeah, I guess just about like recommender systems writ large, because your talk made me think about them. So like if the metric is to just predict the next thing the person's gonna buy, then like imagine you got really good at this and you had, like 100% accuracy.
Mhm.
Like deploying this recommend like so I predict the next thing you would have bought, like had I not deployed my recommendation system. But then I deploy the recommendation system and I get 100% accuracy. I always predict exactly what you would have bought,
Right.
otherwise. And so, like, in fact, I don't change anything at all. Like, this is purely a loss, like, that I had to, like, develop this recommendation system. Um, so, like, if you were, like, I know you're inheriting a lot of these metrics from other people, but, like, would you, like, are these nevertheless the right metrics despite what I describe? Like if you had 100% accuracy because, something better is happening when you only have 3% accuracy, or, like, yeah, like what is it that you really want to optimize for if it's not this?
So the way I see it, this is similar to like in classification, we typically have losses that make the most sense and you can optimize for. But then you have like these kind of on your hand metrics like recall or sensitivity, and these are like some things which you can use to interpret the model. You can't exactly optimize for them. And I think in this space they also have a similar approach. They're kind of trying to minimize the the next token prediction loss. They're not just doing it for the final token. They kind of do a sliding window where they're trying to predict tokens along all the way. So I think it kind of makes sense for the task of sequential or like next item, next video prediction.
Because I would have thought that like really this is sort of like a bandit's problem or a control problem. Like what is the value of a recommendation system in the first place? It is to make you aware of content or products that you wouldn't have otherwise been aware of. So
I
sort of
think
value comes from like recommending things that like you wouldn't have even thought of, like absent
yeah.
the recommendation system. But like once I put them in front of you, you decide that's good.
Yeah. So that's what it's doing, right? In a way, it's doing this collaboratively. Like collaboratively, there's like bunch of items that you have, and there's like sequences from other users or items that you have not even seen, and it's trying to figure out patterns among these, right? Like this is something you might have not even seen, but it fits really well with what you have seen so far. So that's kind of the idea. And so I guess your point is like, how is this data being generated? Is that like,
Or yeah, maybe that's like a good question from like because maybe I'm missing something. I
yeah.
had sort of imagined, and maybe I'm wrong here, that what you have is some like static data set consisting of like users and like stuff they bought.
Mhm.
Um, but that is like if that's what you start with, then you're missing sort of like the control aspect of the problem, that
Right,
by
right.
intervening, you're causing them to buy different stuff.
Yep. So yeah, the thing you're pointing out is like we are missing in academia this online control part of the system. What we have is just some static data set that we measure metrics on. But how it works in the industry is you have these interactions, you learn something which could be a completely different model than what generated these interactions, and then you end up deploying that and monitoring metrics.
And
So
so do you know how frequently it is the case that when you have a new recommendation method that does better on these static metrics, but when you go and deploy it, it actually results in making more money?
yeah, so I know that like on a timescale basis, I think since 2024 there's been a big shift from 2023. There's been a big shift from using just there was this paradigm called two tower models where it didn't care so much about sequences but cared more about like, is this a relevant retrieved item for this query? So think about like searching on the search bar. So most of the models were kind of optimized for search retrieval. Now you have these very personalized session based models. So I think the time scale for shifting there is more like on a yearly base, like maybe 1 or 2 years we see a paradigm shift. But in the day to day, we are always retraining these models, any given model, yeah, with new interactions.
All right, I cede the floor.
Yeah.
Okay. Audience, and then I will mention the committee members, including Aaron. We have a lot more time to ask questions. After that, it will just be. Yeah.
Yeah. Um,
Yeah.
Krishna, you mentioned that in two of the data sets for this last project, short history was better. So I was wondering if it makes sense to just have a hyperparameter where you have a max history length. Even for long ones, you just cut off the history maybe for two most recent items and then predict the performance.
Yeah, that's a good idea actually. I haven't uh, tested that out, but I think it's related specifically to this data set that for beauty and toys, I think there were sports and toys. Most recent interactions mattered more. I think that's the hypothesis. That's another research question we need to test out. I think that is agnostic of the choice of LLM-based recommendation. It can be even tested for like simple matrix factorization or transformer-based recommendation.
And related to that question from online like I saw that recall at 5 was around 6 to 7%, right? I was wondering at what point do we say like this is good enough?
This is a good one. Yeah. I think the point of these benchmarks is you have to beat them before you can even consider deploying it. So in the industry, what I've seen is that we not only measured this, we measured across even different, like you're measuring whether it's hiding sensitive content. There are a bunch of different offline metrics that we use, and it has to be a statistically significant improvement over most of them before we even consider doing a launch, like an experiment, A/B test. Yeah. So, so yeah.
Curious about this semantic rewrites thing you mentioned at the very end.
Yeah.
Curious what happens if you sort of see that as like not a bug, like not an adversarial attack, but kind of as a feature that like
Yeah.
lesser known creators or companies have the ability to like sort of mimic more specific items.
Yep.
Yeah. I'm curious how that interacts with this notion of converging to, because if you're in the setting that you talked about where you converge to this diverse catalog, if everyone's converging to diversity, but they all have incentive to copy what's popular,
right,
then I feel like you don't really have that same thing. So I guess I'm curious for your like broad thoughts on this, and then whether there are any results on these sorts of dynamics in the presence of this like adversarial conditions.
Yeah. So if you look at semantic rewrites, there's been a bunch of work here. The way they model it is that there is maybe a set of 5 target items that they want to increase engagement for. And it's not been analyzed from this item catalog point of view. So all they look at is like a one-step interaction where what should I do right now? Like what rewrite should I do in my 5 text that end up increasing their recall in the users, like that they end up being shown in those users rank lists. So obviously that leads to a degradation in user metrics because we are not, these kind of false items are showing up. But like they have not been studied from the point of view of what does the final catalog look like. So that's like one of the directions I want to look at. Like first, do this for LLM based recommendation, and then as a result, kind of measure maybe how is the in embedding space, how are these item titles changing? Like that is one notion of measuring it without explicitly modeling it as a game, right?
Comment about the first paper. So
Yeah.
you mentioned like that the algorithm is based on like I don't want that.
Yeah.
But why is it more complication, or where do we use Oracle?
Right. So there, what we mean is the experts, which are like each of the group experts, those are the algorithm is Oracle efficient in the hypothesis class for them. So the aggregation is still having a group factor in the runtime, but we assume that the experts themselves is a standard learning algorithm, or we are Oracle efficient in those. Yeah.
More questions from the audience. I think what we will do is and we will ask questions and opportunity. That is